Hello from Ngunnawal and Ngambri lands. My name's Carla Alexandra and I'm a PhD student at the IWF ANU. Malcolm X once said that the future belongs to those who prepare for it today. Deliberately and explicitly including long-term futures in the decisions we make today is really important. We need to account for the future in decisions because the emissions that we make or the dams that we build will have long-lasting impacts on the future. But more than that, I believe we need to imagine a desired future in order to be able to steer towards it. But thinking about the future and planning for it is really hard because the future is so uncertain. There's no facts about the future. And it's also so contested. The future that you may want may not be the one that I want. So why does this matter for water? Decision-making in the Murray-Darling Basin currently lacks processes to account for climate change and other forms of future change. Methods do exist, like foresight methods, such as scenario planning, but we don't have knowledge of how we're applying these in the basin, what's effective, and what needs to improve. And there are calls from practitioners and decision makers for more information on how to apply foresight into water planning. So as an environmental social scientist, my research focuses on how we're making decisions about the future of water in the basin. My research is asking, how is foresight currently being applied for contested waters in the basin? And secondly, how can foresight capacities be integrated into decision-making structures and processes? So foresight is a key concept in my research, and it refers to planning for alternative futures, not trying to predict just one future. Foresight allows people to systematically explore what they want the future to look like, what other plausible futures might arise, and what strategies or policies are needed to help achieve these desired futures. I'm answering my research in two ways. I'm studying processes of foresight in the basin. One process I'm studying is in the Coorong Lakes at the mouth of the basin, and it's part of an adaptation planning process. I'm interviewing participants and project managers to understand how integrating foresight supports better planning for future change. Secondly, I'm surveying the 54 natural resource management organisations in Australia to ask how they're planning for long-term futures. My research aims to generate practical and useful knowledge for practitioners and decision makers. So we need more knowledge on the methods to include the future strategically in present day decision making, and we need to do it in just and participatory ways. A more just and sustainable future is possible for the basin, but it requires us to prepare and plan for the future. Thank you.
I want to talk to you today about my PhD research, which is around understanding the way changes in rainfall runoff will respond under future climates. What we know is that the way runoff occurs from rainfall is changing. We have seen that in southern Australia, where we've seen significant changes in runoff response to the same rainfalls. We've seen some very clear examples in both Queensland and New South Wales over recent weeks where extreme events have occurred that seem to be beyond our expected and observed memory and observed recording. We also know that climate change is not just about changes in rainfall, it's about changes in temperature, changes in carbon dioxide and other greenhouse gas emissions. And it might also lead to changes in things like perturbing events, such as bushfire, such as cyclones, and so on. The diagram behind you shows how I've tried to represent some of those effects at this stage. This diagram is changing as I continue to explore my PhD research, but really what I'm trying to understand is, can we understand what some of those effects are? Do we have tools such as hydrologic models that we can actually apply to understanding how those problems occur or how those effects occur? And are we able to then use those tools effectively to understand the impacts of climate change? In Gunter Blochel's recent paper with many other authors, it was noted that there were 23 unsolved problems in hydrology. Some of those are around issues such as how vegetation dynamics can be understood better and their effects on hydrology, how we use our hydrologic models to understand the dynamics of change, and how we communicate those effectively to decision makers and policy makers. That's really what I want to focus on in my PhD, is trying to understand how changes in rainfall runoff response will occur and whether the tools we have can resolve those changes effectively. And then do we have other tools that we can use to understand the range of futures that may be plausible and the uncertainties around some of those effects? A really good example is how carbon dioxide might affect the way vegetation responds. What we know is that from the literature is that carbon dioxide may lead to a fertilisation of vegetation growth, which may see greater leaf area, which may result in greater interception of rainfall. But at the same time, that same CO2 concentration may cause the leaf stoma, the little openings in leaves, to close up and therefore not be able to release as much moisture in the atmosphere. That in itself is going to reduce the amount of available moisture in the atmosphere for subsequent rainfall, especially at local scale, but could also increase soil moisture. If we have increased soil moisture, we might actually get more runoff. So those synergistic and antagonistic effects can be quite important to understand, especially if we want to understand which ones are most significant. So what I hope to accomplish over my PhD is to understand those issues in greater detail, how useful our tools are and whether we might need to use either different tools or use our existing tools in different ways, and then how we can use some of our decision frameworks to help us understand how best to apply those tools and those understandings in how we quantify the effects of climate change on rainfall runoff. Thank you.
Hello everyone, my name is Yi Yu. My supervisor is Luigi Zanzulo. Today I'm going to introduce my PhD study, which is focusing on the soil moisture high-resolution modeling. Soil moisture is an important variable in the Earth system, which can be used for the regulation of the partitioning of the precipitation into the runoff, infiltration, and also evaporation. As you may know, it has been extensively used in the areas like the drought prediction, precise agriculture, and also the climate change analysis. Soil moisture measurement are many and varied, from the very sparse point measurement, which can be done via the in situ instrument, and also to the very large scale modeling, which is much suitable for the agricultural applications. However, it is not that appropriate to directly apply the large-scale soil moisture data on agriculture. As you can see in the baseline microwave data, in a 10 by 10 kilometer window, you cannot see any information that would be valuable for a localized agricultural application. However, in a same window of the optical data, you can see a lot of details of the ground features like the paddocks and also drylands. Then, how to effectively use the information from those kind of optical and thermal data to enhance the resolution of microwave data would be a research question in my study. Meanwhile, in order to effectively develop a high-resolution modeling framework, we need to transform our understanding on the physical controls like the forcing, land cover, topography, and soil texture data. We need to understand their effects on the soil moisture pattern dynamics at different scales, ranging from a continental scale to a point scale. This might be beneficial for a localized agricultural application regime. So to summarize, this research is to develop a next-generation land surface modeling framework with a hyper-resolution in order to satisfy requirements from the localized agriculture applications. To achieve such a goal, this research will be exploring the spatial temporal variability of the soil moisture and the relevant physical controls across different support scales for Australia. And also, we need to use the satellite observations, such as the thermal and optical data, to enhance the microwave data as a first step towards the understanding transformation. It is expected that research can bring some new insights to the water balancing assessment in Australia, as well as provide some reliable soil moisture data sets to the user community for agriculture and also hydrological use in the key growing regions. That's all. Thank you for listening.
Water is essential to life, so towns often depend on reliable sources of water, such as rivers that always flow. But in 2019, those rivers stopped flowing in some parts of Australia, such as the Darling Baaka River. For some towns, stored water levels declined so much that people spoke of day zero, an extreme hypothetical when there's no water left for the town. On the path towards day zero, there was suffering. Water use was strictly limited, and lower quality water was used as drinking water. And in some places, day zero was reached and bottled water had to be brought in. This situation was at odds with the human right to water. Although we are seeing flooding now, day zero is something we could face again. Water management decisions must be made under uncertainty, and even deep uncertainty where there are multiple plausible futures. Australia has highly variable rainfall that's becoming more variable with climate change, and Southeast Australia is drying. Our rivers have endured decades of water extraction and regulation, and our groundwater is also under pressure. So there are uncertainties in the sources of water, the demand for water, and the costs. This responsibility for uncertainty is shared. Local councils are responsible for water utilities, and they're supported by state and federal government projects. In New South Wales, governments are developing strategic plans and introducing new climate data. However, their water management has been criticised, such as in powerful testimonies from people on the Darling-Barker River and in the New South Wales Auditor General's report on town water planning. So how can we do water planning for towns under climate change better? I'm hypothesizing that adaptive management can be useful. This is the process of intentionally changing how we manage a resource, in this case water, by monitoring the outcomes of decision and learning from them. I'm approaching this in two ways. One focused on individual towns, and the other on how our actions fit together. First, I'll be developing a model that can be used as a practical tool to avoid day zero. My case studies will be towns because they don't have the resources, capacities, and large infrastructure that cities have. I'll explore the different options for water sources, the demands for water, the costs, and potential transitions between options in a future with climate change. Second, looking beyond individual towns, there's a lot of activity around town water security at multiple levels with multiple actors. So with New South Wales as my case study, I'll explore how it all fits together and how the governance can be more adaptive. With changes to how decisions are made, we can avoid day zero and instead meet the human right to water under climate change.
Imagine a future where all children and their children after that could enjoy decent conditions of living. A future in which human society are able to live and co-evolve in harmony with their environment. Well, the road to this future is starting right now, and start with trying to think about how to better anticipate multiple plausible futures in order to prevent our societies to become maladaptive. However, a problem faced by decision makers when dealing with deep uncertainty is that they do not have yet access to future information. They are also facing conflicting views about how to address a problem of interest. And finally, the pace of change is too rapid for them to make use of predictive or forecasting tools to inform their decisions. So how to better support their capability to plan under deep uncertainty? And that's the question that this thesis is trying to address. So based on an historical perspective of integrate models used for planning purpose, one technical challenge of these models will be their ability to convey information that is relevant and that matters to decision makers in order for them to be able to solve a problem of interest. So in order to address the potential issue of uncertainty associated with the information conveyed by models, we develop a critical appraisal framework that enables different model users to reflect on a different uncertainty communication issue that they can identify in user interface and discuss potential solutions with developers. The other technical challenge faced by these models is associated with their ability to accommodate different information needs, as well as to shift from a forecasting use to an exploratory one in order to support a better management of the deep uncertainty. So we develop a minimum information requirement approach for that matters that enable us to customize an existing model so that it can better represent a problem of interest, but also that allow a user to explore the performance of different strategies across multiple future scenarios and to design adaptation pathways. Finally, in addition to these technical challenges, how model will better support decision maker reflection about the desirability of their decision for human society is more of an ethical challenge of these models. So an evaluation is actually underway in order to support the design of a method that is based on a scenario planning process, and more specifically, how to better reflect on the different connection between people and the environment and associate responses to change using the scenario planning process. So overall, through different methodological approach in order to support decision maker capability to plan under deep uncertainty, these theses want to contribute to more just and sustainable future. Thank you.
Hello, my name is Callum Savage, and today I want to talk to you about my PhD research, which is looking at developing an ecological forecast for the Murray-Darling Basin. Now, as I'm sure we're all very aware at this point, the Murray-Darling Basin is under severe ecological stress. This follows decades of over-irrigation in the region, as well as the exacerbating impacts of climate change. Some policy measures have been established to address this problem and return water to the environment. Notably, in 2012, we got the Murray-Darling Basin Plan, which established allocations of water which could be brought back from irrigators and returned to the environment in the form of environmental water flows. But even setting aside the question of whether or not these environmental water allocations are sufficient, we're still left with some really difficult problems. Problems like, how do we identify which ecosystems are most in need of environmental watering? How do we weigh up trade-offs where we have to choose one ecosystem or one system over another? How do we ensure that the water being delivered is sufficient to initiate, for example, a water bird breeding event? And perhaps even more pressing, how do we actually measure the success of these environmental water allocations and ensure that they're actually achieving the results that we hope that they achieve? Currently, this process is not sufficiently transparent and not underpinned by any objective measures. So in my PhD thesis, I certainly am not proposing to solve this problem, but I am hoping to address it by developing an ecological forecast for the Murray-Darling Basin. So what is an ecological forecast? Well, basically we can think of it like a weather report. What it does is it will give us an assessment of the state of the ecosystem now and in the near future, say on a seasonal basis. This is important because it lets us assess the impacts that releasing water into the environment has directly and in real time using fresh data as soon as it becomes available. This also lets us weigh up competing policy alternatives. For example, we can model what different water release scenarios would look like and what impact they would have on the environment. And perhaps most importantly, it lets us look at the basin as a whole in a single model and address the basin's water management holistically. Now, actually developing and implementing such a forecast is an enormous task and well beyond the scope of a single PhD. However, what I'm hoping to do is lay the foundations for developing an eco-forecast across the Murray-Darling Basin and hopefully contribute in a small way to increasing the transparency and evidence base for environmental water allocations in the basin and contribute to a sustainable future for these important ecosystems. Thank you.
Climate change is one of the major challenges in ensuring sustainability in the agriculture sector. In Bangladesh, rice is the staple food of the citizens, and this crop is highly affected by flash floods almost every year. Since long, extension services have been helping farmers adapt to various farm-related challenges by providing farmers farm-related information, technologies, and developing farmers' capacity by connecting them with various organizations, institutions, knowledge, and resources. However, there is little known how extension services can help farmers adapt to flash floods. In this context, my research examines the role of extension services in helping farmers adapt to flash floods in Bangladesh. My research explores how extension services can connect farmers with various formal and informal organizations. Here, the formal organizations might include the stakeholders from research organizations, financial service organizations, and informal organizations and actors might include neighbors, the friends, and relatives of farmers. Moreover, my research also investigated how extension services can support farmers' learning to adapt to flash flooding. Here, learning is a process where farmers share their knowledge, ideas, and experiences about flash flooding with other farming actors and stakeholders, and interact with those stakeholders to gain a better understanding on the ways of adaptation to flash flooding. In addition, my research also explored the capacity of extension services to help farmers adapt to flash flooding. The findings of my research can be applicable to other countries which have been facing flash flooding stress in farming sector, including Australia. In addition, the findings of my research can also be applicable to other climatic stressors conditions in the farming sector, such as droughts. Thus, the findings of my research can advance the understanding on helping farmers to adapt to various climate-related stressors in various countries and various contexts. Thank you.
Should we action leakage alarms like we click on login warnings? It has become an essential part of existing with computers. We all get delivered messages like this from websites. They detected your login, but due to some uncertainty around it, requires some extra validation to continue. Most of the time it's a false alarm because you know it's you signing in. We all know the annoyance of having to click away the boxes and get back to our work, but deep down we are glad that there's some system in place for stopping a disaster. In any warning system, designers must consider the following balancing act: how to action the alarms we are certain about, remove confusion around false alarms, and what are the risks of missing an alarm. Well, this balancing act is present everywhere, from unusual logins to the highly automated engineering of irrigation networks, where my interest is. Automated irrigation networks can contain thousands of kilometers of channels, each with sophisticated gates to regulate the water, all providing real-time telemetry of many parameters. This has allowed engineers to implement a huge amount of alarms and warnings to indicate when sensors or automation is not functioning as expected. In my research, I've been looking at new ways of exploring the real-time data for these networks and turning them into meaningful information that can assist with the changing of the network for more efficient and reliable water delivery, all without the confusion. While automation of networks has brought huge water savings, there is still very high uncertainty about how, why, when, and exactly where the water goes missing. Understanding these uncertainties and their information is essential to better prepare our irrigation systems and their impacts on the entire water cycle as we undergo future drought. And so my first project was to investigate the reasons around water going missing in the irrigation networks, that is, closing the water balance. I implemented a proof-of-concept leakage detection tool that could bring meaningful information around water balance anomalies. Using a simplified model of the system, it could reliably detect leakages under the high uncertainty of water delivery. Through this proof of concept, I looked at how leakages I found would impact the planning of maintenance and how I could integrate with the gold standard alarm philosophies to minimize the operator overhead for actioning leakages. Right now, I'm looking at what we can learn about patterns of leakage across the entire network and how we can use that to direct infrastructural change. With these learnings, I'd like to see how leakage information can communicate with other available models, tools, and data to not only action anomalies by measuring the fingerprint of leakages, but also to see how this information can feed into a larger understanding of the irrigation system with model-based alarming and digital twinning. Have you noticed that some login warnings are only raised if your account is being accessed from a new location or device? Well, what excites me is that the goals that I have are not unique to irrigation. My work can be inspired and can contribute to the other industries all around the world that are looking to increase the understanding through the growth of interconnected models, datasets, and processes. Thank you.